In this chapter, we're going to look at linear systems in three variables. So, an equation in three variables defines a plane. So, for instance, this equation right over here in x, y, and z may define this plane. And on this plane, there are some points. So, if you take any one of these points and you plug the x and y value into this equation, you will get a true statement. So all these points satisfy this equation of this plane. And of course, there are other planes here. So we have three planes. So we have a linear system in three variables. So what we're looking is a solution. We're looking for one point, one point that will solve, that will solve the linear system, and that point will be on each one of these planes. So if you look for a point that is on each plane, right, or common to each plane, right now we don't have one, right? There is no point common to each plane. They all have points, but not in common. So let's look at some other configurations. In this one, by the way, I forgot to mention when a linear system doesn't have a unique solution, we say it's inconsistent. So if there is no point x, y, and z that satisfies all three equations, we say it's inconsistent. Here we do have some points in common between, let's say, this plane and that plane right here, and all those points, there are many, and they represent this line. So any point on that line. And you have to understand that these planes are infinite, right? So I'm just showing a portion of this plane. So this line, any point on that line could satisfy the equation of these two planes. And any point on this line will satisfy the equation of this plane and that plane. But still, we don't have a point that satisfies or that is on all three planes. But we're getting closer. Okay. Let's try look at another configuration. So we got all the planes now intersecting, at least with one other, and the same thing, like this plane and that plane has all these points on that line common to both planes, right? So there's infinite number of points that satisfy those two equations, but still we don't have one point that satisfies or that is on all those planes. So finally, we come to one configuration. Well, actually, not yet. Sorry. In this one, we have all three common to this one line. So we say this is consistent because, hey, we have some points that are common to all three. The problem is, though, there's still a lot of them. You see this line? So if I pick a point on any point on that line, it will satisfy all three. We say it's consistent because you now have a solution to all three, but we say it's dependent because there are many solutions. So that can happen. In the final, or next to the final configuration, we have, in this configuration, we have, if you notice, we have these three lines, again representing the points in common, let's say with this plane and that plane, and we have the other three lines too, but they all intersect. My computer just went out a little bit. They all intersect at one point. So if you look at, I think I twisted it around. Let's see, I think this is better. All right. So if you look at these three lines right here, right, they intersect right here in the middle. That is one point that all these three planes have in common. So finally, we come to a solution, to a unique solution to our three equations in three variables. So we call this consistent and independent. One unique solution. It doesn't have to be at right angles either. I have these at right angles. If you notice, they're all at right angles. But if you tilted them a little bit or rotate them a little bit, you still get the same thing. So, oops, let me hide the layer. So if you rotate this around, there's just not one configuration for this to happen. There are many configurations. So in this one, you see it's the same situation. We have lines, three lines that are common to two planes, but they intersect at one point. So that one point is a solution to the linear unique solution to the linear system.